Hi guys, this is Yao from Xidian University, China. I'm happy to share our work on this conference. Our paper title is Active Attack that exploits biometric similarity difference and basic countermeasures. Biometric authentication combines multiple smart sensors to identify individuals by using human behavioral characteristics such as fingerprints, faces, human voices, and handwriting. Such biometrics have been proved to be unique. Different people have different features. One of the typical examples is gait recognition, which has matured in recent years and becomes a low-cost and reliable method for authenticating users. Based on that, applications based on biometric uniqueness are increasing, so it's essential to ensure the robustness of the authentication system. Here's an attack example. Although biometric-based authentication systems can balance security and usability, they also face many security threats. Imitation attack is more efficient and less disruptive to the system. However, unlike other biometric features, the various data related to gait can be collected in our public lives. By learning the victim's gait and training their data, the attacker has the same state as the victim within authentication systems. Authentication systems often use Euclidean distance to measure the similarity between template data and the incoming data. It measures whether the similarity score is lower than the predefined threshold. If it's lower than the threshold, we determine the incoming data to be an attacker. In our work, we are inspired by a mathematical theory called cookie sequence. We are wondering if there are some multiple attackers. Would the similarity between the attackers become higher in the training of imitation of a specific victim? To investigate our guess, we invite 20 well-trained men from honor guards to join our research. Before participating in our research, the participants have gone through quite a long goose step training. We combined the goose step with the gait of ordinary people to design our work. We use same action method to train all participants and then use their gait after training to make comparisons. If the false acceptance rate in our experiment is increasing, the effectiveness of our attack is indicated. This figure shows the effects of our attack in the existing scenario. The horizontal axis is the gait period. The vertical axis is the Euclidean distance between the gate and the template. The lines in the figure represent the distance or cost between the participants and the victim's gate template. The blue line is the evaluation of one participant of the victim with the template. The other four lines show the best performance of the corresponding attackers. The smaller the distance, the higher the similarity with the victim. From this figure, we can see that attacker 1 and attacker 2 has a higher similarity with the victim than attacker 3 and attacker 4. In particular, attacker 1 shows better performance at multiple sampling points than the victim. It also can be seen from the figure that it's difficult to determine a value as a threshold to distinguish attackers and the victim. This figure shows the distributions of the distance of 4 attacker-victim pairs in all attempts. In the figure, the horizontal axis is the distance of the participant's gate and the template. The vertical axis is the distribution density. After a training period, the previous gate recognition system based on acceleration values didn't distinguish between attackers and the victim by using a threshold. In other words, our attack can confuse the system to produce misjudgment. According to the performance of our attack, we need to study the reasons behind the result. All the participants in our study formed muscle memory of the gate through long-term training. Thus, all the participants can avoid the problems of irregularity that is existed in previous work. The result shows that participants have stable performance. Furthermore, the gate we designed has become the participants' own. The gate details used in training are well quantified, and the training process includes single training and collective training, which avoids mutual compromise during joint training. Only using acceleration value as a feature will be vulnerable to deal with our attack. This figure shows the differences of direction in a gate cycle between victims alone and victims with attackers. From this, we can see that based on the victim's gate template, that is red triangle and the orange line, the attacker's performance is more chaotic than the victim's. Therefore, we believe that we can use the force direction as an essential feature for identity verification. The primary function of data preprocessing is to convert the raw data into usable gate cycles. At first, we extract working data from raw data, and then we use SG filters to filter out significant portions of the high frequency content and noise, and minimize the error while maintaining waveform and heat. The next is gravity separation and cycle extraction. Finally, we remove cycle pairs that had a significant deviation from the distance. Before our comparison, we need to align the coordinate system of new data with the template. We will reposition the form before the data collection each time. This causes the offset in the position and the twist of the orientation. We found that within a gate cycle, the direction changes at about 50% to 80% of the stage, which is very regular. Most of the sampling points are distributed on the big circle. In that period, most of the sampling points are on the big circle. For different participants, the distance in a cycle is that part is significantly shorter than the remaining part. That is, most of the points is less than 0.2. Therefore, for this reason, we use that part to calculate the continuum and use the entire cycle to get the distance. Since the attacker doesn't need to mitigate a specific victim in our scheme, we can select the best performing attacker-victim pair for evaluation. This figure shows the confidence scores of the best performing attacker-victim pairs for authentication. As mentioned, we recruited 20 participants. We collected 3 different gate data from them. One is gate of their own. The second is our train style, and the third is the good style. We collected 10 sets of data for each participant's gate and finally divided them into about 1,200 samples for each gate. Then we used tenfold cross-validation machine learning-based method to measure the performance of participants. Compared with the previous multi-sensor authentication system, using such as random forest algorithm, our results have comparable precision and recall rates as our figure as this table shows. We summarize our work. In our work, we propose and implement a novel attack scheme to evaluate the reliability of the gate recognition scheme. We designed and implemented an Android application to record the user's gate data. Although human cannot imitate other people's gate, we have proved that it's possible to successfully attack a specific gate verification system. Based on that, we propose a new gate authentication scheme to defend against this attack and upgrade our application. Simultaneously, we have a major issue. Our system requires users to keep the phone stable in the pocket. In future work, we plan to solve some related problems. We plan to infer some physical information of the phone holder based on the acceleration data. Moreover, we want to know how long it takes to learn and adapt to a new gate to pass a specific gate verification system. Thank you for your listening. Thank you for your listening.